Are we ready?
Yes.
Okay. So welcome to this laser physics course. My name is Hamish Mcnair. I am the Director of Clinical Education for Candela in the Europe, Middle East and Africa region. During this presentation, we're going to be discussing the basics of laser physics, looking at different wavelengths, pulse durations, etc., and how lasers interact with tissue. The word laser is an acronym, and it stands for light amplification by the stimulated emission of radiation. In order to understand how a laser works, let's first do a quick review of some of the terminology that makes lasers possible. So here we're going to be looking at atoms, photons, spontaneous emission, stimulated emission, and also amplification. Atoms of any substance are made of electrons, photons, and neutrons. The nucleus is where you find the protons and the neutrons, and the electrons sit in orbit around this nucleus. So the electrons of the atom can either be in a resting or an excited stage if stimulated by a photon. So as you can see in the resting stage, it sits in the inner orbit, and as it becomes stimulated or excited, it moves into the outer orbit. Spontaneous emission, this happens once it's raised to the excited stage, and the electron naturally tends to return back to its resting stage, and it does this once it's emitted a photon. And this photon emits is similar to the one that it's actually absorbed, and this is what we call spontaneous emission. So then we move, when we have this excited stage, the electron absorbs a second photon, and now because it has two, it needs to emit these two photons, so it's able to move back into its resting stage, as you can see, so it's moving back into the inner orbit. Amplification, so this is basically where we're generating the laser beam, and this is where we have this stimulation of this emission repeated innumerable times, so millions of times, carrying on and on and on, so we're producing more and more and more photons. And this is where we get our laser light from. So let's look at the physics of laser light. What is laser light? So laser light, doesn't matter what the wavelength is, laser light is always non-ionizing, and I'll explain this a little bit more as I go through the presentation. And we have three unique properties that separate laser light from any other form of light, whether it be a light bulb or an IPL system. First thing is it's monochromatic, it's also coherent, and finally it's collimated. And because of these factors, a laser beam is very easy to manipulate, and it can expand and it can focus very easily, which allows us to focus it in on whatever it is we're trying to treat. Here we have our electromagnetic spectrum, and in general terms, the majority of lasers that we're using within medicine or in aesthetics are sitting either in that visible light range, which is between 400 and 700 nanometers, or we move with some of our systems into the infrared range, which is above the 700 nanometers. This is the electromagnetic spectrum, and as you can see, this is a very busy slide, because what we're trying to show here is the different types of lasers with their wavelengths and what different areas they absorb into. So you can see on this chart we have melanin, we have hemoglobin, we have deoxidized hemoglobin on this chart, and you can see, depending on the wavelength you're using, will determine what the absorption is into that particular chromophore or color. And as a company, Candela's platforms utilize this spectrum, particularly the visible part, as it's recognized that different laser medium material is able to produce different wavelengths that can then target the multiple colors or chromophores at their peak potentials. As I said before, laser light is a non-ionizing radiation. So unlike nuclear radiation or gamma rays, we don't mutate the cells. Whereas if you're using nuclear radiation or X-rays, in these circumstances, you actually get mutation of cells or death of those cells. But very importantly, with laser light, we don't have that issue. Laser light is a single color, so it's monochromatic, and it's one wavelength. So if you take an ordinary light bulb and you shine it through a prism, as the light passes through that prism, it breaks up that light into its individual constituent colors. So in essence, you shine that light through a prism and you see a rainbow of colors being shown the other side of the prism. However, if you take a laser light, and in this case, we're using a yellow light, you shine it through the prism and you only get yellow light being emitted the other side because that's the only color the laser is made up of. Laser light is also coherent, and this means that the light waves are all in phase with one another because they're the same wavelength. So if you look at the difference between an ordinary light and a laser beam, with a light bulb, you have the light coming out in all sorts of different directions. It's many different wavelengths, so it's not a single color, and it's not what we call coherent. So you can see in these images that we have different wavelengths, and they're all moving in different directions. However, with a laser beam, we have all of the light traveling in a straight line. They're all a single wavelength, so you can see they're all in parallel with one another, and they're also coherent because each one of those peaks and troughs of that wave align with one another. It's also, laser light is also collimated. So same thing here, we're looking at using a torch or looking at a laser pointer. So if you take an ordinary torch and you shine it on the wall and you're maybe half a meter from the wall, you get a circle. And as you move further away from the wall, that circle starts to increase in size because that light is not collimated and it's diverging. Whereas if you take a laser pointer, it doesn't matter at what distance you are from the wall, that spot remains the same size because the light is collimated and it runs in parallel. And what we do with our systems at Candela is we use some kind of a focusing lens, so we're able to manipulate the spot size of whatever laser we're using, determined by what it is we're trying to treat. Here we look at the difference between a light bulb or an intense pulse light unit versus the laser. So in conclusion here, light bulbs are what we call polychromatic because they contain many colors. And because we have all these colors together, we actually see this as a white light. They're incoherent, so that all of these beams are not running in the same direction. They're all split up and defocused in essence, and it's less intense when compared to a laser. Whereas, as I said before, the laser is single color, so it's monochromatic, and it's coherent, which means all of those wavelengths are all in phase and parallel, and it's also very intense. Let's now look at the components that make up a typical laser. So you need, in essence, 4 things to produce a laser. You need something we call a lasing medium, and I'll discuss this in more detail in a moment, an optical cavity, a power source, and then finally you need a delivery system in order to deliver the laser light you're producing within a machine actually to the area that you're trying to treat on the skin. So you can see we have what we call a laser cavity, and within this laser cavity, we have our lasing medium. We also have our power source, which is stimulating whatever our lasing medium is. And at each end of our laser cavity, we have one, on the left-hand side, we have a total reflector or mirror. And on the right side, we have a partial reflector, which will have a shutter in it, which allows us to deliver that laser light from the laser cavity. So the lasing medium is the substance that's responsible for producing the laser beam and the specific wavelength of that laser. And we have a number of different types of lasing mediums. We can have gas, which is typically something like argon or carbon dioxide. Solid medium lasers, so these are crystals, so you could have a ruby laser, or more likely an alexandrite or an Nd:YAG crystal. And then we have liquid, which is, for instance, the V-beam, which is also known as a pulse dye laser. The dye being the clue in the name because this is using a liquid. And with our V-beam, it's a rhodomin dye that we're using. And this energy is stored in the lasing medium in the form of these excited atomic or molecular energy states. And once we stimulate these with a power source, they become excited, and then they start to emit the photons, which is where we get the light from that we can then use in order to treat whatever condition it is we're looking to treat. The only difference here is diode lasers create their laser light electronically, so they don't have a lasing medium. Power source, we need something that is going to stimulate our lasing medium in order to produce all of the photons to give us the laser beam or the light. And typically, we can use 3 different ways of stimulating this, our lasing medium. We can use electricity. So a good example of this would be with our core CO2 laser, where we're using radio frequency energy in order to stimulate the carbon dioxide. We can use flash lamps. So an example of this would either be the Gentle Pro series or the V-beam, where we're using a high intensity flash lamp in order to stimulate that lasing medium. And the other option would be to use another laser in order to stimulate the lasing medium to produce our light. And an example of this would be our peak away system. So once we've actually excited the lasing medium and we have the photons, we now need some way of getting that laser light from within the optical cavity to the tissue that we're trying to treat. And there's 3 different ways that we can do this. We can use an optical fiber. So here we have a fiber optic cable. The light will be passed along that fiber optic cable to the end of the handpiece to the tissue that we're treating. We could also use an articulated arm. And here the laser beam is actually running up the center of a hollow tube. And then at the articulated elements, we have mirrors. So we change the direction of that laser beam, and eventually the beam will arrive at the handpiece. Or the other option would be a fixed mirror. And this is typically something you see with diode lasers, where you have lenses and mirrors within the handpiece, which directs the beam directly onto Here is our optical fiber. And in this example, we're using it with our Gentle Pro series. So the light, or the laser light, is produced within the system itself. Then the light passes along this fiber optic cable to the handpiece and to the tissue that we're treating. There is a small amount of power loss when you're using a fiber optic cable, and this is referred to as attenuation. And generally, for most visible wavelengths, this is less than 10%. So we don't lose a large amount of power or energy when we're delivering it through a fiber optic cable. The next option I spoke about is the articulated arm. And we commonly use this for wavelengths such as erbium YAG or CO2. And this is because both of those wavelengths will absorb into glass. So if we try to use a fiber optic cable, we would actually shatter that fiber optic cable and we wouldn't be producing any light at the end of the handpiece. And the second area where we're using articulated arms is for a laser that has very, very short pulses and high peak power. Because again, with a laser of that type, if we passed it through a fiber optic cable, we would shatter that cable because of the short pulse and the very high peak power. And an example of this would be a picosecond laser. So from Candela's point of view, the picowave. Let's now look at laser parameters. There are 4 basic parameters you always need to think about when you're looking at lasers. First of all is the wavelength. The second is the pulse duration. The third is the spot size. And finally is the fluence. So a wavelength is the distance from one peak to the next peak, as you can see in this diagram. And when we're talking about lasers, we discuss short wavelengths and we also discuss long wavelengths. And the difference between a short and a long wavelength is, with short wavelengths, we have what we call high frequency. So as you can see, in a given distance, we have more of the peaks, and we also deliver a higher energy with a short wavelength. And conversely, with a longer wavelength, it's lower frequency because we have less peaks within a given distance, and generally these deliver lower energy. Here we have the chart you saw earlier on in the presentation. So what we're looking at here is choosing a particular wavelength that has an absorption into whatever our chromophore is. And this is why we're not able to use a single wavelength to treat everything. We pick the optimum wavelength to treat a particular chromophore or color. And this wavelength is obviously determined by the lasing medium, as we discussed earlier on. It's measured in nanometers or micrometers, but more commonly it's in nanometers. And a longer wavelength will penetrate deeper into the tissue until we get beyond approximately 1100 nanometers. So if you're moving from a 1064 nanometer laser, so an ND-YAG, down to a 595, so for instance our V-beam, the penetration will become less as that wavelength gets shorter. Once we move above the 1100 nanometer range, then water becomes the main chromophore, so the main absorption of the laser. And therefore, particularly when we're treating tissue, because there's such a high volume of water in the cells, we are much more superficial in our absorption because all that energy is absorbed within the cells very superficially. And I think this is a very useful slide to demonstrate the different depths that different wavelengths go into the tissue. So you can see on the left-hand side, when we start with a frequency doubled ND-YAG at 532 nanometers, very superficial. It will treat superficial telangiectasia and very small vessels. But once the vessels become slightly larger and deeper in the tissue, it isn't able to treat that deeply. So you can see we then move to a pulsed dye, so the V-beam at 595 nanometers, which allows us that little bit more depth of absorption to treat more vessels. And then moving up through the range, we see the Nd:YAG 1064. So this is penetrating much more deeply into the tissue, which means we're able to treat leg veins, for instance. And then moving at the far end to the right of the spectrum, the CO2 laser becomes much more superficial because I mentioned before, the main chromophore here is water. The pulse duration. So this is, in essence, how long the laser is pulsing for, and it can also sometimes be called time on tissue or TOT. And depending on the system, this is either expressed in milliseconds, in nanoseconds, or even in picoseconds. And very often the pulse duration or the exposure of the light onto the tissue is the key to actually defining how we treat and how efficiently we're treating whatever our target might be. And here we look at the principle that long pulses can heat large volumes of tissue and shorter pulses confine the heat to a smaller volume of tissue. And as an illustration, if you think about a very small vessel, so for instance, here we're looking at an espresso cup. When you put this onto the stove and heat up that very small volume of water, it heats up very, very quickly. And then you make your coffee, but if you leave your coffee just for a couple of minutes, you find that it cools down really quickly. And conversely, if you take a kettle and put this on the stove with maybe 1.5 liters of water in it, this takes much longer to boil. And then you make a much larger drink, and it takes longer for that bigger volume to cool down again. So the principle of pulse duration is basically the same as this. So if we're treating very small targets, we use short pulses. And if we're treating larger targets, then we need to use longer pulses because the volume is bigger. So therefore, it takes longer to get sufficient heat into that bigger target to actually destroy it. The energy, when we're using lasers, we measure in joules. However, commonly, we actually refer to the energy being delivered by the unit area. So we call it fluence. And this is measured in joules per centimeter squared. And the power of a laser, and this is actually measured in watts. And in general, for most lasers, we prefer to talk about fluence rather than watts, except when we are discussing, for instance, a continuous wave CO2 laser. But in general terms, you will see the useful information basically is the energy which we're measuring in joules per centimeter squared. And the more the fluence, so the more energy that we're delivering, obviously this means we produce a more destructive effect on the tissue. But we then have to remember that the relationship between the fluence and the spot size of the laser is also important. And the larger the spot size, the deeper into the tissue that light will penetrate, and the more effective we are at deeper depths within that tissue. This is true up to a certain point. So as an example, if we're looking at an alexandrite or an Nd:YAG laser, the maximum penetration into the tissue occurs somewhere between the 15 millimeter and the 18 millimeter spot size. So once we move up, for instance, with our Dental Pro series to a 24 millimeter spot size, that doesn't penetrate any deeper in the tissue than the 18 millimeter does, but it allows you to cover the area more quickly because obviously the 24 millimeter is significantly bigger than an 18 millimeter. And finally, let's look at the tissue interaction. The goal of any kind of laser treatment is we're looking to destroy whatever our primary target is. And this could be a vessel, it could be pigment, or it could be a vascular lesion. And we do this by heating it to a high enough temperature that we actually destroy our target, however, not damaging the surrounding tissue. And this is a principle called selective photothermolysis. Initially discussed by Rox Anderson back in 1983. And in essence, he says that a laser light of a specific wavelength can destroy a target containing the adequate chromophore or color without damaging the surrounding tissue. So what's happening here is the majority of that laser light is being absorbed into whatever our target might be, and less of that laser light is being absorbed into the surrounding tissue, depending on what it is our target might be. And this is done partly by looking at what's called the thermal relaxation time. And this thermal relaxation time needs to be longer than the pulse or the duration of the laser pulse. And he defined the thermal relaxation time, or the TRT, as the time it takes a target to cool down by 50%. And this is through transfer of the heat into the surrounding tissue via thermal diffusion. So in essence, we heat up the target, and as we're heating it up, that heat is already starting to dissipate or diffuse into the surrounding tissue. So we normally, this is why when we're looking at different size targets, they will have a different thermal relaxation time. Larger targets have a longer thermal relaxation time because they take longer to cool down, and smaller targets have a shorter TRT because they cool down more quickly. So in order to assist in this selective photothermolysis, whereby we want to destroy our target, but we don't want to damage the surrounding tissues, another way we do this is by using some kind of cooling. And there are three basic methods that we can cool tissue. We can use contact cooling, we can use an air cooling system, or we can use cryogen spray or dynamic cooling devices, we call it in Candela. So contact cooling, here, as the name suggests, we have a cooled sapphire plate which comes into contact with the skin, and we cool the skin down by conduction. So this cool plate starts to cool the skin down. Then we fire the laser light through the sapphire plate to heat up our target, but we're not heating up the surrounding tissue. The second option is air cooling. So in this example, what we're doing is we're using some kind of an air chiller unit. We're blowing cold air onto the skin in the area that we're going to fire our laser light, and this is known as convection. And finally, cryogen spray or dynamic cooling, excuse me. And with this, we spray the cryogen onto the skin, and then we have a small delay before we fire the laser. And during that small delay, we get evaporation of the cryogen that's on the skin, and this is what cools the skin down before the laser light is fired. And again, very precise in exactly the area that we're going to fire the laser. And in many instances, using dynamic cooling allows us, particularly on a vascular situation, to use very high fluencies very safely. So my final slide, and again, very, very important slide. This is looking at the Fitzpatrick skin typing. So Dr. Fitzpatrick, the doctor based in the States, who came up with this different types of skin types based on, really, it's not just the color of the skin, but it's more important to think about how that skin reacts to overexposure to sunlight. It can be in the early days when people start using lasers or IPL machines to make the mistake of purely looking at the color of somebody's skin and from that determining which skin type they are. But you really have to think about how their skin reacts when it's exposed to the sun rather than just the color of the skin. And as you'll see with all of our systems and virtually every laser you find in the market, we all have some kind of a treatment guideline, and all of these treatment guidelines are based on the Fitzpatrick skin typing of the individual that you're treating. So if we don't get our Fitzpatrick skin typing correct, then all of the other parameters that you're putting into the system are potentially not going to be correct because you haven't got the first parameter right at the beginning. So that concludes the course. And any questions?